Hello, hello.
So good morning. The first speaker of this morning session is Luis Renato Fontes. He is our colleague here in the institute, and he will speak about contact process under renewal course.
Thank you, Rodrigo. It's a pleasure to take part in the workshop, and particular to learn in more detail your recent work, which is, and your collaborators, which is quite nice and challenging. So I believe your idea of having this immersion in the issues around your project is, for me at least, it was very good, because it's really need to look at these things very closely. In any case, my talk will be about the contact process. So it's kind of only loosely related to statistical mechanics, so this is based on joint papers with co-authors here. So Domingos Marchetti is here, and so many of you know most of them here, and so this is where they were published. There's a survey which is, in case you want to look at a sort of informal account of the results. There's a survey in this journal here. It's a journal of the Brazilian Mathematical Society. Okay, so let me explain the model. So the context, I believe many of you don't know about it. So let me just try to explain it. It's the model for the spread of an infection, and it was proposed by Harris. And it works as follows. So it's a dynamical model. So it's there's a space dimension, which is represented here by the horizontal line, and there's a time dimension. So you may think of it as if you want to think about it in statistical mechanics terms, it's a two-dimensional model. Time is a second dimension, so it's a further dimension. So in general, our results many times are for the space as ZD. Okay, so the space is going to be ZD. Okay, and so in this picture, this is equal to 1. Okay, so in ZD, so in Z1, in this picture, we have individuals resting at each site of ZD, of Z here, and then they are resting forever. They don't move, the individuals. What changes is their health status. Okay, they can be either infected or healthy. Okay, so if you want to think in statistical mechanics terms, it's +1 and -1. And so they interact, but the interaction is sort of asymmetric, okay? So the interaction goes as follows. So I will use this term, this language of infection and healthy, because this is the what people do in this context. So it's so initially you have say infected and healthy individuals, and they are and when the individual it gets cured at certain times, and when they are infected, they may spread the infection. Okay, so so the cure mechanism is as follows. You put timelines over each individual or over each site, and in these timelines you put these marks here, these crosses, okay? And these crosses represent health instance. Okay, so if so X was infected initially, so at this time it will get cured. Okay, and then and so it becomes healthy afterwards, and it may get reinfected. Okay, and if it's infected, so this one here, suppose W here is infected, so at this time here it may spread infection across these edges here. So you have these crosses in these edges. These crosses and edges, this configuration of crosses and edges determine the evolution of the model, okay? And also the initial condition. So how do we put these crosses and edges? So the crosses are going to be put here according to renewal processes, independent renewal processes. Okay, so this the distance between these crosses, so the intercure times here, if you want, are IID random variables. In principle, they are general. Okay, positive random variables in the context of renewal process. Okay, so it's a general renewal process. All right. So in the case of Harry, so Harry is in '74. When he proposed his model, he put these crosses according to a Poisson process, okay, which is a renewal process if you want, with exponential inter marks, okay, and the how do we put the infection edges? So the infection edges are also in the case of Harris, and in our case also, are going to put according to a some point process. Okay, so you may think of timelines here between the in the edges of the of ZD, if you want it, of Z1 here, and you put you may think of so this is x and this is x plus 1, and here is x plus a half. So this is so you put Poisson processes here also, so marks of Poisson processes, and these marks you put the edges. Okay, all right. So this specifies completely the distribution of the marks, the cure marks and the infection marks. Okay, infection edges. All right, and then how the model works. It's so suppose you start with a single infected individual. Also, so W here at time 0 is infected, and all the other guys are healthy. Okay, so the time starts, and then at this time here, there's an edge, infection edge, so W infects its neighbor, it's Y, okay? And then, so at times progresses, at this time here, then Y infects Z, so at this later time here, W gets healthy, this later one here, Y gets healthy, and before infecting anyone, and at this time here, Z becomes healthy, and the infection is killed. Okay, it goes extinct because there's no more. Everybody now is healthy, so there's no infection spread of the infection, right? So a healthy individual doesn't spread the infection. Okay, when it meets an edge, it doesn't. Nothing happens. Okay, so. But of course, there might be another edge here, infection edge. So this is another configuration where there's an extra edge here, which is this blue one, dotted one here. And for this configuration, that you see that the spread survives up to time t. Okay, so at time t here you have these two guys here, which are infected, and all the others are healthy. Okay, and so the issue here. So one thing to pay attention to is that the infection spreads along these paths here, which could be called infection paths. Okay, and so So one issue that comes up immediately is whether there's a positive probability that the infection will survive forever. In this context, we talk about survival. So survival means survival forever of the infection, which can be also termed in terms of existence of the. So that started with a single individual. Okay, so let's suppose we have a single individual, and then the infection rate die out almost immediately if the cure mark before an infection mark for W, and then you see that there's a positive probability that no matter I mean there's always a positive probability for infection to die out starting with a single individual. Okay. But the issue here is whether there's a positive probability that it will survive, okay? Okay, and so the question that we want to ask here is further. So this question about the survival. Of course, it depends on the parameters of the model, right? So parameters here are the distribution of T and the value of this rate here, of this infection rate, okay? So Harris, paper by Harris in 74, he showed that for small values of lambda, in case of the distribution is exponential of rate 1, okay? The cure distribution is exponential of rate 1, okay? And so his result is his first result is that for small values of lambda, there's the probability of survival is 0, and for large lambda, it survives the survival. Okay, so you may think of this model as a percolation model, right? So it's a sort of oriented percolation because there's an orientation, there's a time orientation here. Okay, there's no spatial orientation. There's time orientation. So you may relate this model to oriented percolation in Z2, for example, in this case. And actually, the way to show that for large lambda there's positive probability of survival is a percolation argument. It's a Piles argument. Okay, in the discrete setting. So you compare this, you discretize this model in time, and then you get a discrete oriented percolation model, and you do a Piles argument. Okay, so it's the usual Piles argument, but for the oriented case. Okay, so you see already some connection with statistical mechanics kinds of arguments. So let me proceed. So our question is then not about existence of the probability of positive probability of survival for large lambda, but whether this may happen for all lambda. Okay. In the case of Harris, if lambda is small, then the probability of infection surviving is 0. Okay, so our question is conditions over T, right? So here we're asking that something happens for all lambda. So this is so this will involve the distribution of this intercure variable T, okay, which determines the distribution of the model, right? Because all the variables here are the same distribution. Okay, so this should depend on the distribution of T. Okay, in the case of Harris, where T is exponential, we know that Harris proves that lambda is for lambda positive but small, its probability is 0. Okay, so So if this phenomenon here takes place, we talk about persistent survival. Okay, so it's just a name that was, I guess, introduced by Chuck Newman and a collaborator, Volchan and Sergio Volchan. So persistent survival here means that this phenomenon here, that probability that the infection started from a single individual survives forever, is positive for all values of the infection meter, okay? No matter how small, but positive, of course. So I told you before that this doesn't happen for the usual contact process, high-risk contact process, where T is exponential. So there you have a critical parameter, okay? Where below which there's probability of survival is 0, and above which it is positive. But we are not looking at this situation. Okay, we just want to know whether there could be probability 0 if lambda is small. Okay, in this kind of model, and of course it should depend on the distribution of t, as I told you before. And if you think for a moment, you will more or less come to the conclusion that it's probably related to the tail of this distribution, of large, heavy tails for distribution. Okay, and this is of course the case. So before stating a positive result for this question, let me just make the remark that Newman, Volchan, and Chatterjee and Duret, they had this kind of phenomenon appearing in contact processes a bit different from ours. So the case of Newman Volchan, it's the contact process random rates, and the usual contact process, the exponential cure contact process, but with random rates. Okay, and in the case of Chatterjee and Duret, they get this for the contact process on random graphs with power law degree distributions. Okay. So this is somehow in all of these results, this long tail, this heavy tail is important. It's crucial for the appearance of this persistent survival. Okay. So this somehow has to do with long tails. Yes. Yeah, the rates are quenched. Okay, so they are fixed initially, and then you look at the tails of the rates. Okay, if the rates have some heavy tails, I mean, you have to formulate the model where it's either close to the origin or infinity. I can't remember. But then you get a similar phenomenon of as I will show you in a second, happens in our case. Okay, so it's a sort of long tail phenomenon in every case. So in the power law random graph case, also you have that, right? Because you have sites with many edges. Okay, and along these edges the infection spreads more easily. Okay, all right. You have these large hubs, no? So it's a similar kind of phenomenon. It's a long tail kind of phenomenon in every case. Okay. So so there's a related paper also by these authors here, Ilario Ungaretti, Valesini, and Valles, which succeeds all our papers, but this one was published before our last one. But they consider renewal marks also for the infection. A renewal process is also for the infection. So not only for the cures, but also for the infection. They get similar. They study similar issues and related results. In their case, the phenomenon is persistent extinction, which is extinction for every value of some parameter or other. Let me not elaborate, but it's there have similar ideas in both papers for some of the results. No, their paper have many more results than only these issues of persistence. Okay. So let me go to our first result, which is sufficiency for the occurrence of persistent survival. So as I told you before, you may you expect that a heavy tail is crucial here, and we have this condition here that the tail of this intercure distribution is heavy tail in the sense that it's bounded from below by a polynomial factor of t, where alpha here is less than 1, okay? But in particular, this means that the expected value of t is infinite, okay? And we need some regularity conditions, which I will for the tail of the further regularity conditions for the tail, not only this bound, but let me not try to go into this. I'll explain perhaps a simpler case, which is the case where t is attracted to an alpha stable law. So attraction to an alpha stable law means that the tail of the distribution of t is of the form L of t divided by t to the alpha, where this L of t is slowly varying, okay? Slowly varying, okay? So this so this has much more regularity than this condition. These conditions generalize this quite a bit, but let me, for the purpose of explaining some ideas, let us consider only this case. We have an extension for the case where alpha equals 1, but then we need to require that this slowly varying function increases very fast at infinity. Okay, it's slowly varying, but it has to. There's okay, but it doesn't matter. I'll try to explain the ideas behind this, simple ideas behind this result for this case here, where we know quite a bit. It's a classical subject. So to understand the classical results used behind used in this key ingredient for the proof. So so we want to show that there is a positive probability for the existence of an infection path going from the origin to infinity for every lambda. Okay, for every value of infection parameter, no matter how small. So then we have this tunneling event here. So remember that we have independence of the renewal processes and also of the cure infection marks. Okay, Poisson process for everything here. So this tunneling event, which is something that takes place between two spatial positions, Ln and Ln plus 1, and they are morally independent somehow. Yeah. Let me not talk much about. But so these Ln's they are random and they are of the order of n. Okay, and they are so the distance between Ln and Ln plus 1 is just how many inspections you want to make along the timelines between Ln and Ln plus 1, such that you will find this interval here, this time interval here between 2 to the n and 2 to the n plus 1, completely empty, okay, of cure marks, okay. So you have an empty large interval here, and so this is going to favor the spread of the infection. So if you get to this interval, then it's easy to continue the spread of the infection. So starting from the origin, you get to here or to here, then it's easy to I mean, you have ample space for ample opportunity to spread the infection. Okay, so this the thing is that why this distance between these two guys is relatively small. It's just this comes from the heavy tails of the of the model. Okay, so in this sort of renewal process of long tails, if you look at a large time and you look at the distance between the neighboring the neighboring marks, they're going to be very large. I mean, this is the inspection paradox, right? Even though the distribution of the inter-cure marks is fixed and independent, the the distance is when you look at the interval that has time t, this is going to be large. You know? This is the so-called inspection paradox. Okay, so this is in this case of heavy tails, the order of magnitude of these intervals here, all of them is 2 to the n. Okay, so you have just to go some distance of order 1 in order to find a large an interval which is larger than 2 to the n here. Okay. And once you have that, and again using heavy tails, it's easy to show that no matter how small lambda is, we will find with large probability, we'll find a staircase of infections like this. So in this event here, if this first interval is infected, the staircase will conduct it in an oriented fashion, even to this other one. Okay, and then if the probability of this event is quite large, so large that you can multiply all of these probabilities for every n, and it's still positive, then you get your survival. Okay, because no matter how small lambda is, you will always have a positive probability to go for the infection to spread until a certain point, and from that point on, you get this tunneling phenomenon taking hold. Okay, so this is basically the idea, and so in the other more complicated. And there are the other conditions, more general conditions. It's a similar idea, okay, but it gets more complicated. So in the same way, so this picture is showing that you may, under heavy tails, like we in our conditions, you get a sort of this tunneling event going forwards, right? Going in the direction of infinity in an oriented way. Okay, so so for the basically the same reason, you also get the infection to go backwards. Okay, because it's more or less the same phenomenon, right? So as soon as you have survival, so this leads to the following result. So which is sort of a what it is literature is called complete convergence. You look at the configurations. So let's look at the of healthy and infected individuals at time t. Okay, so you're looking at the distribution of the status of health of individuals at time t. So at site x, the individual is going to have status 0 if it is healthy and 1 if it's infected. Okay, so in this case, you get a configuration of status of the individuals, and then you get if you look at the evolution of the status of all the individuals along the time, you get a process, or it's a Markov process. I mean, in our case, it's not Markov. It's because of I mean, in the case of Harry's, it was because of the lack of memory of the exponential cures, right? But in our case, it's not. But in general, it's not. In any case, it doesn't matter. I mean, so what our next result says is that no matter how you start your health status at time 0 for the individuals, you only, as time progresses, the distribution of the health status is going to be either all individuals healthy or all of them infected. Okay, it's a bit different from the usual contact process where you get a result like this, but in the case of survival, the distribution here is non-trivial. In our case, it is trivial. It's everybody infected. Okay, and this is related to survival. Okay, if the model doesn't survive, the infection doesn't survive, of course, at a certain point, everybody will get healthy. So you'll get the distribution, everybody healthy. Okay, and, but if it survives, then what's going to happen is that everybody around the origin, say, becomes healthy. Okay, and the mechanism is exactly the same as the one, or is very similar to the one before. So remember the tunneling events, right? So in this case where we are conditioning on survival, of course, because if model doesn't survive, then clearly everybody gets healthy. Okay, but if the model does survive, the infection survive, then what it's easy to believe perhaps that the tunneling phenomenon will imply that the interval here from 2 to the n to 2 to the n plus 1 is going to be infected with high probability. And once it's infected, then you get sort of backwards there. It's exactly the same argument for the forwards there. You get a backwards there of infection. So you get everybody around the origin infected. Okay. So this is more or less almost the same result as I mean, of course, the argumentation can get involved. I mean, the conditions for this second theorem is they are a bit different from the one before. Here, I'm explaining only the case, or trying to convince you only based on this initial distribution of T to the alpha stable or attracted to alpha stable distribution. Okay, but our conditions are a bit more restrictive. Okay, so we demand a polynomial upper tail also for the. Remember, here we demanded a polynomial lower bounds for the tail, but for the second theorem we demand also an upper bound. Okay, a polynomial upper bound also. For this one. Another refinement is what we call the closeness to determinism, which is when you can. I mean, you see that things here tend to be simpler because you get this large interval, and once you have those large infected intervals, they tend to spread the infection easily. Okay. So in face of this, we can say a little more about what goes on with the distribution of the process. So let's look at the status of the health status individual at site X. It doesn't matter; it could be the origin here, okay? Because the model is translation invariant, okay? And so now we're going to condition on the history of the cure process, okay? The only random here is related to the spread process, and also, but here we're also conditioning we're conditioning on. We should be conditioning on survival. Yeah, so here we're conditioning on survival. So tau here is the extinction time. So tau equals infinity means that the process survives. Okay, and so we're conditioning on the history of the cure marks and also on the event that the process survives. This event here also depends on on the on the spread variables, right? Edges, right? So there's a it's not only no, it depends also the probability depends also on the spread on the edges, edge variables, but only through these events here that you're asking for survival. Okay, and so so I have two results. One for when the tail is very heavy. So for this result, we are in this. We need really a lot of regularity. So we ask that our intercurrent of variables are in the basin of attraction of alpha stable. Okay, have this form. Okay, and, so there are two cases when alpha is less than a half and alpha is larger than a half. Okay, when it's smaller than a half, then it's very heavy-tailed, right? And when it's larger than a half but smaller than one, it's not so heavy-tailed. And case of alpha less than a half tail, there are other regularity conditions which I won't bother you with, related to the theory of the renewal processes, and which we need to use. I mean, in our arguments, and so the results is as follows. Let me show you it in a picture. It's probably easier to convey the idea. So you're looking at this. So there are two pictures here. Let's concentrate in this left picture first. So this is for the case alpha less than a half. Then the other ones for the alpha larger than a half. For alpha less than a half, then the model is very heavy-tailed. And so what happens if you look around? So you're conditioning on the cure marks, okay, and you're conditioning also on survival, okay. So what happens is that if you look at time t at site x, and you look backwards, you can look at the age of what's called the age of the renewal process, which is the distance between time t and the last cure mark, okay. And then, so this is a random variable, okay? So if you take time very large, what's going to go on is that this y of t, I mean, this is could be or further one, right? But what with large probability what you're going to see in the neighboring positions here, neighboring sites, you're not going to see. You're not going to see cure marks, okay? You're not going to see cure marks. They are very far from thinking of time t, large t. So these cure marks for these other neighboring timelines are very far from t, okay? In the neighboring positions, okay, with high probability. And then what's going to go on? And they are going to be infected because they are conditioning on survival. And then with high probability, they're going to be infected. So in order for you to look, so the status, so at this time, you know that immediately after this time, you know that X is healthy. But what goes on in this time interval here depends on whether there appears in terms of infection of X. It depends on the appearance of edges in the infection edges from the neighbors, right? So what you get is this first result here, which is the probability that X is infected at time t is just going to be the probability that you find edges from neighbors in this time coming from the neighbors at this time interval. So this is what's written here. What's behind what's written here? Okay, but if alpha is larger than a half, so you have heavy tails, but tail is not so heavy, then here we need to demand also that there is a positive probability that the for the intercure distribution. There's a positive probability in every neighborhood of the origin. We need that. You'll see why. In this case, this statement is not true. Okay, So the difference between these two things can get large, can get bounded away from zero infinitely often. Okay, and the reason is as follows. So if alpha is not too small, it's larger than I have, then you will find that at random times, you will find these patterns of cure marks very close together, very forming a sort of pack of large pack of cure marks at some site, at some neighbor site of X. Okay, so and if there appears an infection mark here, which would in principle infect X, then X would be infected at time t. Okay, but because of this closed back configuration of cure marks, whenever there appears a mark, an infection mark here, it happens when the neighbor is healthy. Okay, so there's no infection to spread. Okay, so this happens with positive probability for arbitrarily large random times. Okay, and so this means that we don't have the same phenomenon as here, and we can refine this, and if you go above alpha equals a half to 1, I mean alpha varies from a half to 1. There will be transition times where you find a single pack like this in the neighborhood, to 2 sites or to 3 up to 2 these sites where you have close pack. So you get a more refined. You can say more than just saying that it's different from this, but you can say what it is in these situations. Okay. And okay, so this let me. There are some results for finite. I mean, so far I've been giving you arguments that are they're good for infinite graphs. So, but I mean, when you have these heavy tails, you can more or less imagine that you don't need to have an infinite graph in order for since you have these large intervals, large hubs spreading the infection, you don't need the graph to be finite. And so we have results for finite graphs, but let me not go into this because otherwise I won't have time to talk about results for the opposite result, not persistent survival, but the usual kind of survival, that is the probability being 0 for small enough lambda. Okay, lambda close enough to positive, but close enough to 0. Okay, and for this we need, of course, I mean, you can imagine that you need some condition on the you need lighter tails, right? Or a light tail. Okay, so the condition on the tail that we put is this one, the tail of the distribution of the intercure variable. Okay, so we put this condition here, which is a little more than the first moment. Okay, and so under this condition, the probability of survival is 0 for all small enough lambda positive. Okay. So we had a previous result here where a condition was a little more strict, but then this is sort of an improvement of this result in this paper that required much more. I mean, a bit more than in the moment situation, required strictly larger than 1 moment. I mean, this function here is lowly varying, so it's smaller than any polynomial, right? So this is more strict. It is not a big deal, this difference here. But the big deal is that between the results from 20 to 23 is that we don't need one dimension, and we don't need other regularity conditions on the tail of distribution of T. And so when you have a second moment for the distribution of T, then there are simple comparisons to branching process, which appeared in this paper. So let me try to give you I don't know, maybe I'm already out of time or close to. So just to give you a quick idea, I mean, this is the perhaps more closely related kind of argument to sort of statistical mechanics. It sort of involves some sort of multi-scale reasoning. So let me just try to explain you very quickly. Perhaps it's going to be difficult to be very quick, but let's start. So the idea here is to connect relate the survival event to which is an infinite event, to an event inside some rectangle, okay, space-time rectangle, and then once we have that, we may try to perform some sort of this analysis, okay. So we start with this object here. Pn is just the probability. So we fix this rectangle of base 2 to the n and height 2 to the. So it's a two-dimensional argument, a picture, but it works in all dimensions. Okay. I mean, so a rectangle here of scale n is base n and height 2 to the n log n. So we're asking that in this rectangle we have either a. So these paths here that I'm drawing here, they're infection paths. Okay, the red paths that we saw before. These are infection paths. So in this event, we are asking that there's a halfway upward crossing here of a infection path, or a full lateral horizontal crossing here of this same rectangle. Yeah. Okay, and we take the soup of these probabilities over all the. So this is times 0, so the base here is times 0, and we are asking that these events take place. We take the soup here over the initial points below this renewal starting points below this time. This is important because in the renewal situation we don't get independence, right? In the exponential situation, you can forget about what goes below here, but not in the renewal situation where you get some correlations here coming up. So, but in any case, so we relate now the probability of survival to these quantities here, okay? The probability of survival up to time 2 to the n log n, okay? So the probability of survival of the model starting at the origin. So this interval, this rectangle here is based here on an interval which is centered at the origin. Okay, so there's a so if the model survives up to time 2 to the n log n, either you have a completely full crossing here, a vertical crossing of this rectangle, or have a crossing that goes out at either here the left or the right. Okay. So these two events here, of course, have the same probability by of the symmetry of the model, and so we get you can upper bound this probability here by Pm plus 2 times the probability of a single of these lateral exit events. And then we want to relate this probability to some Pn, okay? Of course, I mean, this first event can be upper bounded by Pn, right? But the other one, it's not so clear, but let us do that now. I mean, you just cut this rectangle here in the middle, bisect it in this way. And so you immediately see that this event here implies, I mean, there should be an implication here, implies that either you get, for some subrectangle here, so one point here is that when we cut this interval, it's the base of scale n so minus 1 too, so you have to cut these intervals, this rectangle into, and the number of cuts here is less than order n, okay? And so you either have a full horizontal crossing here for these for one of these subrectangles of the scale, right? Or a lateral crossing or a vertical half crossing, okay? I mean, of course, the vertical half crossing is implied in this, is included in this situation. So it's either this or that, okay? So it's at this point that we need the half crossing, okay? That's the difference between this result and the previous result I mentioned, where we didn't use these half crossings. So we can relate the probability of survival up to time to the n log n to Pn plus a constant, which you can take as 1 or any constant you want here, positive, n times p to the n minus 1, right? Because the n comes from the number of rectangles, which is actually smaller than n. Okay, it's n to some power smaller than 1, but we can put n here, that doesn't matter. But then it's scale n minus 1, right? And then, so finally, in order to prove our result, we just need to show that this object here converges to 0 as n goes to infinity, okay? And so these, so let me just perhaps be very brief about this. So Pn involves horizontal, vertical half crossings and horizontal crossings, okay? And so let's look only at the vertical half crossing, okay? So this is the rectangle at scale n, so base 2 to the n, and height here is to the n log n. We cut it in, we know that there is a half crossing, so there's a infection path from the base to this position here. So we cut these subrectangles, okay? And of course, once you have these half crossings, you have full vertical crossings of these 4 rectangles, okay? So let's look at what happens in one of these rectangles, right? So in this rectangle, we have a base 2 to the n, but the height here is 2 to the n log n minus 3, okay? So we want to adjust for the scale, okay? So wants to relate this event here of this vertical crossing to crossings of rectangles of smaller scales, okay? So I mean, in order for you to have these vertical crossings here, you have these 3 possibilities. Either you have these vertical crossings of these scales of rectangles of scale n minus 1, or you have these lateral crossings of rectangles of scale n minus 2, okay? In any case, let me not go into much detail. When you put this all together and use the same kind of argumentation that I gave here, you get this bound for the upwards crossing, and then you see that in here I have 4 events, right? So I just I gave a upper bound for 1 event. But I mean, if these events are independent, we'd be finished, but they are not because of the renewal processes, which propagates correlations along in time. Okay, but we can just look at these 2 rectangles. So if we look at these 2 rectangles and events where you have fewer marks in this lower rectangles here. I mean, once you have clear marks on all the timelines of these rectangles here, the first and the third, you uncouple these two events. Okay, so this is where this event here comes, where we are asking that there is you can find crosses, cure marks along every timeline of these previous rectangles. Okay, so once you have that, now we finally get we have a similar result for the spatial crossings, and it's easier because you don't have these correlations in the horizontal, the space direction, right? So this is we finally get this sort of recursion scheme. We can iterate it up to some all of these things that I told you briefly are true for large n, so we can iterate this up to some n0, and then so in order for our scheme to work, I want to make sure that the probability of an event at the first n0 rectangle is good, and so let me not elaborate on this, but this is it's at this point that we take lambda small, right? Because in order for us to be able to iterate this to a good end, we need the initial condition to be good in some sense. The probability of the initial condition is small. Okay, and so this is obtained by taking lambda small. This n0 is large, but it's fixed, so you can now take lambda very small. And so one last thing that I would like to say is that we have to control the probability of this event here. Remember, the AN event is the event that you don't find cure marks in any timeline, in any timeline in a rectangle like this one, the first one, okay, and the third, okay. And for that we need we need the bound of the this bound here. We need this condition, okay. This condition enters in guaranteeing that the probability of AN here, this thing that is crucial for the uncoupling, is quite small, exponentially small, okay. And so in the end, when we iterate everything, we get an exponential bound for Qn, and that's what we needed to prove to get the result, okay. And sorry for being late. Thank you.
So comments or questions? No. So if not, so let's thank Renato again.
bom, so assim, tá bom? Tá. Já vem. Então tá. É o meio? É. Aqui no meio. Obrigado.
So, okay. So the next speaker is Domingos Marchetti from the Institute of Physics here, our neighbors. And he will speak about the hierarchical and vectorial model in the bigger or equal 4 limit loss of total spin via renormalization group. So thank you.
Thank you. So I would like to thank Rodrigo for this opportunity to meet some friends, collaborators, and people that are neighbor. And we use it to share this semi-interesting. So this is a joint work with William. William was a former student, and so I would like to say something that we have been working with his subject of his subject, essentially. So there are many words that some people have mentioned. For example, hierarchical, or is any vectorial model is, I will explain. Looks like easy model. And also, I'm interested in the limit law is something like basically is the central limit theorem for the model, statistical mechanics model, in particular this one. Well, this model, any vectorial model, is related to another famous model, which is called spherical model. And the spherical model was introduced by Berlin-Katz in the 50s. And the spherical model is a really simple model that exhibit phase transitions. I will talk about not much about the physics of this model, but after that I can give some reference or some link that you can find more detail about what I'm talking in this lecture. And the spherical model is not a kind of easy model. It belongs a different class of models. It's a mean field model, I would say, but it's difficult to see the connection with mean field, but certainly has some relation to mean field. But the kind of phase transitions that occurs in this model is a kind of condensation. So the physics, the phase transition is some sort of condensation of zero mode. I think some people here may have heard about this phenomenon of condensation of zero modes. The spherical model will play a very strong role for what I'm talking about, but me interested in some lattice model is not necessary because I'm looking for hierarchical, so it's a long-range interaction that it doesn't need to be supported on the lattice, but it's better to look at a lattice. Any vectorial means instead of having a spin model, which we have just two directions. Any vectorial means a vector in any dimension. So it's a kind of easy model, but the spin is living in a sphere of any dimensions, and the relation to this is the relation with the spherical model is related to the way that we take n to infinity. So it's a spin that lives on a sphere in any dimension, and I will let this dimension to infinity. So I want to start with the model, which I call any vectorial model. Is we have an equilibrium Gibbs measure. The degree of or the spins, I would say, like in the Ising model, is more suitable to see the variables living in a space of r to the power n. Small n means the number of sites inside the box, the finite box. And the capital N always means the dimension of the spin. And so it's more suitable to look at not vector itself, but to look at our variable in R to the power, to that power. So I call this, a configuration would be a number in this space. So X here is a configuration of this space. So we have an equilibrium measure is the usual Gibbs measure, exponential of beta times the energy of a configuration. And because the spin is on the sphere, it's appropriate to use what we call a priori measure. So sigma n is a uniform measure on the sphere. So if we just choose n equal 1, is the Ising model, the usual Ising model. The sphere has only one direction, so the uniform means equal probability of having +1 or -1, n equal 1. Right, but in general, this measure, a priori measure, just makes a choice, uniform choice on any dimensional sphere, and also it's appropriate to the radius varies with n. Since we are taking n to infinity, so it's appropriate to find the limits for this measure to make this sphere change with n. the radius of this sphere. So the interaction energies is like this model is a two-body interaction. It's a ferromagnetic model, so its interaction is always positive. I don't introduce the beta here. I put beta here, but I can change beta also together with the scale of the sphere. I think I will do that after that. So far, this energy is the usual spin model, a two-body model. Now, for the spherical model, actually is very simple to solve for any interaction. Well, I would say for many interactions. Essentially, the interactions that you can diagonalize, essentially, for example, like in Fourier, transform Fourier. To look at the interactions that has translation invariance or whatever, you can use it Fourier. But the choice here is important. I choose it to be hierarchical, the interaction. And I will talk a little more about hierarchical interaction. So the interactions which happens here is it's called J. That's J is the one that makes the model to be ferromagnetic. But when we look at the spherical model, it's more appropriate to see interaction matrix. Here I'm talking to, maybe I should tell, here X is a vector, so it's a vector on R to this power. J is a matrix, right? And this is okay, this is a product, a scalar product of these two matrices, or two vectors, right? So it's more appropriate to use the hierarchical Laplacians instead of the interaction, because that is related to the spherical model. I can simply introduce this identity matrix using the fact that each spin satisfies the spherical constraint, and this spherical constraints is just can be written in terms of this inner product x times inner product with x equal to the square equal to the n is the constraints. So I can just introduce in the energy with no, it's just a constant that may be introduced. So it's so you can deal not with this interaction, but using what I call the hierarchical Laplacian. It's Laplacian because the way to look at the Laplacian is that we have to have a positive spectrum of this matrix, and they also include in the border of the spectrum the zero. So it's I told that there is a condensation, the zero modes, and it's important we have a positive interaction and to have this zero mode also. And the hierarchical here is comes from the usual hierarchical model introduced by Dyson. I think it was mentioned that Dyson introduced this model. We can just write this hierarchical Laplacian using what is called block operator. So is this block operator just make blocks. L is some integer larger than 1, and then we divide the lattice, the original lattice of space 1 to the block. A block of size L, and then this operator just says that we block in make block in all scales. The power here k means that we are going to make this block spins in all scales, and the scales varies from 1 to k. So that's the usual way to write the block spin. I use a normalization. This is suitable to understand the hierarchical. And okay, so the choice of hierarchical is one possible, as I said, for the spherical model, because what's important is that we are able to diagonalize this hierarchical Laplacian on a lattice. That's enough for the spherical, but for the n vectorial, this is crucial, right, to be hierarchical. So the easy, what make easy with the hierarchical is that we can find exactly all the eigenvalues and eigen vectors that diagonalize this matrix. And the eigenvalues are written here, and there is a huge multiplicity of, because of this blocking. This is the multiplicity of the eigenvalues, but the zero mode is just multiplicity, has multiplicity 1. And just also have to mention that hierarchical Laplacian has the usual property. For example, the hierarchical Laplacian generates random walks on ZD in such a way that it's recurrent if D is less or equal to 2, and transient if D is larger than 2. And D is corresponded to the usual spectral dimension. Then, if the spectrum is discrete, but you see that there is this huge multiplicity, and it accumulates close to 0. And then in such a way that if we look at the neighborhood of the zeros, the way that accumulate, besides to be discrete, is such that we can count the eigenvalues and divide by the size, the log of the size, and then find that this is really the spectral dimension, right? And that's because that's explained, huh? That's explained this property. So it's important, this property, because in the spherical model, I'm about the spherical model for dimension d larger than 2, strictly larger than 2. The other thing I should mention before at the beginning is that I'm interested. As you see, there is no boundary conditions in this energy, or in other words, we're working with free boundary conditions, as you can see here, and the reason I'm interested in to characterize the fluctuations of these random variables at the critical point. And because I'm working for d larger than 2, strictly larger than 2, always in the critical point has only one equilibrium state. So it's not sensitive to the boundary condition, the situation that I'm talking about. They're different from other talks that has been done where this study is first order transition. Here is the second order transition at criticality. Okay. Okay. The usual way to deal with this spherical model, I think the most appropriate one is to look at use saddle point methods to describe the thermodynamics and also to describe phase transition. I'm here writing this saddle point method for the N vectorial. Here we the saddle point method and also the quantity that I would like to study is related to the ratio of partition functions where I introduce a external magnetic field. This external magnetic field just means that I choose a direction of its where I point my magnetic field. I have a sphere of any dimensional sphere. I choose any direction of this magnetic field. So here is H is a scalar, but is behind this is that I can choose any direction, right? There is no magnetization that on the critical point there is no magnetization, so I have a full symmetry involved. And then when I introduce this magnetic field here, this ratio here is basically the generating function of the moment, basically. So the object I would like to study is the behavior, how this behaves, and basically for d larger or equal to 2, this behaves like a Gaussian. D larger than 4, larger or equal to 4 behaves like a Gaussian. This expression. So the usual way to make this saddle point is do Laplace transform, then perform Gaussian integrals, and then invert the Laplace transform, use Melan. And then Melan introduced these integrals on the complex plane. Eta can be any number, and the integral has to do from minus infinity to infinity in the imaginary direction. There is this phase, and then because it's Gaussian, right, it can be explicitly written this way. So the saddle point can be used as well. But the part which I would like to use here is, and use the spherical model, is the fact that if I look at this ratio of partition functions that I would like to describe how it behaves in the limit. Any large K measure how many hierarchical distance I have in my box. So for large box, and is the way that I can relate these partition functions, both at the top and the bottom. The bottom has no magnetic field. Using upper-lower bounds, and the upper-lower bounds are the spherical model. Let's just say spherical model, I mean, also let me go back a little bit here. Spherical model means instead I have one spherical constraint for each site, for each spin. Spherical means that I will make a constraint for a vector in this space, spherical constraint to this space. So instead of having each side a constraint, there is only one constraint for the sum of all variables. So I look for vectors, constraints for the vector here. One just constraint, not for each site, but for all. And that would be what's called spherical. And so the point here is that this representation, either this one or I can write in this way also, is the same. It's the same way. Here it means just Gaussian integral is the same expression. And this expression here, I can use infrared bounds to bound the partition function for above. And this expression here, I can bound the partition function for below using Jensen inequalities. So I think this is the usually way to deal with this any vectorial model, is to find the upper and lower bounds, for example, for the ratio partition function, or for the logarithm of this partition function. I have upper lower bounds. So in this way I can look at the fluctuations more precisely using information from the spherical model. So most of question that I will talk about is related to the spherical model, not to actually the model, because the spherical lower upper bound. Another comment is that this lower upper bound can be very sharp. So I can use even to look at the to deal at the criticality of the model. I will comment that. Okay, so I mean, also there are two ways to look at this problem. One way is to look at the ratio of partition function, uses saddle point methods, and bound from below and from above. And the other way is to look straight model. That is exactly a hierarchical model. And once we have a hierarchical model, we have what is called explicit recursion relation to the a priori measure. At the beginning, at k equal to 0, the a priori measure is just uniform on the n sphere. But then, using this recursion relation, we look at the a priori measure of the blocks. So this is the first block, but these recursions allow to do multiscaling up to the kf level of the hierarchical model. So hierarchical model are important, as I said, because we can use a very strong, powerful method, which is called renormalization group. And this renormalization group acts in this a priori measure. A priori measure. Here is a priori. So that a priori measure tells what happens at a very large volume if we take k large. And so that recursion relation was introduced by Dyson, but then there are many other people that study. Blair Sinai in 70s, Ekman Collet 70s also. They look at this recursion relation for easy model. So it corresponds to n equal to 1 discussion, right? But I'm interested in this n vectorial and the n large, very large. And then this only was investigated by Gawędzki, Kupiainen in the 80s, but the best results that I need basically are developed by Kozycki in the 90s, right? This guy has a very nice approach, correct approach to the n vectorial model. But not by looking exactly to this recursion relation, but the one that I'm writing here. Gawędzki, Ekman Collet, Blair Sinai usually investigate this recursion relation, but there are one way much better to study fluctuations. That is better to look to the characteristic function of these measures, a priori measures. And if we do Fourier transform for the equilibrium measures, then these recursion relations goes to this form. And this form means if we just apply, if we just apply it here, Fourier transform, and the Fourier transform of convolutions becomes the convolution product of the Fourier transforms of each one of these guys. And if we have a product, usual product of this measure with the Gaussian measure, then this is equivalent to the heat kernel. So if we just apply right Fourier transform of this transformation, we get this expression. So this expression means that instead of look at this convolutions, the convolutions means what means these convolutions? It means that I sum all the spins, the block, we do blocks. And we divide also for some power, not decay. And decay. When we look at the block spin variables, what we are doing is just some random variables. Of course, they are not independent. And they're independent in each block, but the blocks are connected through the interactions. That's the interactions. So these are basically the convolutions due to this block spin. And then the distribution is a convolution. So we are fixing the value of the sum. And this term here is the power that I choose to normalize the sum. Of course, I'm looking for the critical point, so I normalize it not by the central limit normal normalization, but at criticality fluctuations are strong. So that is, I have to divide not for L to the D over 2, but larger, L to the D over 2 plus 1. So that's the size of the fluctuations. It's abnormal. Abnormal normalization, right? And then when we look at here, we see the characteristic functions to the power LD. There are LD terms in this convolution in the sum, and here is just the normalization. And this term here is just means the heat kernel. I have to evaluate the heat kernel, and here it has the wrong sign. I have to evaluate it to negative time. And that's basically the recursion relation that I use also, like Kozycki. That's the one that I use. And so I'm going to talk to some other simple model, hierarchical model, which consists in take the block size to 1. Here, it doesn't make sense to take L to 1 here, but when we do Fourier transform, here I'm free to take L to the 1, L to the 1 limit. Most of the work we have done is to show that all limits that we have performed here are continuous, so the expressions can go on. And actually, we first have done in this limit our result, and then we stand for L, any L now, and it can recognize all good properties that I have I will mention here. So this is called approximation, but actually it's not an approximation. Hierarchical, I think, is an approximation already, but that's is some choice and was introduced by Felder in '87, and he shows that we are able to take this L to 1 and the number of interaction k to infinity together such a way that this quantity is fixed equal to t. So that's a t, a time. Time means continuous varying scaling, continue varying scaling. And in this continuous, we end up in a PDE here because we are looking at the log of the characteristic function of the a priori measure. Then, because of the logarithmic, instead we see a heat equation, we see a Hamilton-Jacobi equation. And these two terms here this is the scaling and this is the power associated to, well, the power becomes one term and this is the scaling. So these two terms added to the Hamilton-Jacobi. This is basically is the heat when we look at this logarithmic function, and the two terms are scaling and the power term. The final term is that we need to fix some conditions that at zero. I want this to be a characteristic function, so I have to divide. It's the ratio of the. I'm looking for the ratio of the partition functions, and then the characteristic function has to be normalized to 1 when z equal to 0, and so this term here is guaranteed that the evolution equation keeps the property that u at z equals 0 is always 0. And then we have to look at this from the point of view of a normalization group. I wanted to look at the evolution starting from the initial condition. Initial conditions is the uniform distribution. I calculated the characteristic function of uniform distribution in a IME sphere. Oh, this is classic, but not trivial. Our work tried to do some reviews where all details has been done about this. So that is the usual characteristic function of IME sphere developed by, I don't know, maybe Schoenberg have done this before. So J is a spherical Bessel function. That's the initial conditions. I have to take log, and this is our initial condition of the dynamics. As I said, I'm interested in the limit law. I needed to take k to infinity. I will talk about the spherical model, how the spherical model is related to this problem of PDEs. But as I said, I can follow the same steps using the discrete model also. It's easy to see that the Gaussian means, as I talk, I take a logarithm. And so Gaussian means is equal to z square. The z square is a stationary point. So I'm looking for the trajectory starting from the initial conditions, which is a spherical model, And then I want to follow this renormalization group up to infinity. And at critical point, right, at the critical point, I expect for G larger than 4, including 4, goes to 0. It's easy to see that we can find linearize these equations and see eigenvalues, eigenvectors, and linearize around this Gaussian. And then we can see that the stable manifold has codimension 1, so it just fix the temperature. As when you fix the temperature at the critical point, then we are able to make this converging distribution. In other words, I will see convergence of the characteristic function to the Gaussian, right? That's the statement. Now, I would like to stress this point that a trajectory, that's something that was not reachable for a long time ago. Let's see here, any of these works, Blair, Sinai, Ekman, Gavensky, Kozycki itself, never start far away from the Gaussian, always look at the neighborhood of the fixed point. So the fact that this is typical of, I would say this is bad, it's not a good things to the method of renormalization, but because renormalization say there are many models that has a universal class that behaves in the same way, but class before any investigation of hierarchical model and never included the real model that we wanted to discuss. The real model is the one, the model, for example, any vectorial model is the one that we start from the initial condition far away from the fixed point. So basically, what I would say here, the basic analysis that I have done is, maybe I can summarize to not go too further, is the following. I have upper lower bounds for the any vectorial. I have the model upper and lower bounds are very sharp. That I'm able to do in detail, the renormalization group is starting from the initial condition is the spherical model. And then I know that the spherical model, I can start from the real model or whatever. I know that there are many models that goes to there, but enough to see the model that I wanted to study. And then they drive all along very close to the neighborhood of the fixed point. And when you are in the neighborhood, this is a standard analysis. There is no problem. The question is to make, including in this analysis, initial conditions that really are physical, initial conditions like easy model, for example. That's is something that only has been discussed very recently, right? I made it there. But essentially, don't know. Would you like? I have some time. Oh, okay. Maybe I can tell more about something more about. Okay, so that's the theorem. The theorem is that I'm able to take n to infinity. First, this spherical model. This is the spherical limit first, then t to infinity. But as I said, the bound is able to not to take n to infinity, but any large and t to infinity. And then it doesn't go to this Gaussian, but it brings us close as I want to the Gaussian. And then from there, standard analysis can be done. For n infinity, there is a very nice paper by Ben-Arose, Irinivi, Muchanov, but it's for example. And then it's a nice large deviation analysis for hierarchical model, and he's able to discuss high temperature, low temperature, and also critical temperature. So that was the beginning our interest in to use the spherical model to make bring that we are interested into the neighborhood. So this Muchanov is an interesting paper. Watanabe has also been done this. This idea also has been done by Watanabe, but Watanabe is hybrid. He imports some result from Kupiainen, and there are ideas that we took from Watanabe, but we don't follow him. We follow this idea from above or below, or using perturbation theory, one of it. And the investigation of n infinity was done by myself, Guidi and Conti, and we have done this a long time, in 08, in 2008. But also, it's for infinity. We have done some experiments of not so rigorous. The way we've done is very well controlled, thanks to this paper. There is some things that I would like to mention, that there are ingredients that we use. The fact that we keep the n invariant, the equations, the initial condition satisfies this invariance or n invariant. So it's such a way that we can use the radial coordinates. The other question is that there is only power. The function is even in model in the norm of Z. Though this even is also preserved by the dynamic, normalization dynamic. And we are interested also in any large. And we have done asymptotics. For the initial condition, we have very control, but not for the dynamics. Our dynamics fail. At least it is some part of this conclusion. Borel-Sum ability of the power series cannot be recovered from the dynamics. This is we quantitative. We have done something, but not conclusive, and that's why the reason that we come back. Other things which plays very important question is the fact that the ferromagnetic, the model we allow to use stronger properties of um, Lee-Yang properties. We used to call peak class. Peak class is equivalent to the Lee-Yang property, but it's further. It's a generalization because are looking for any large, in particular n infinity, and then Lee-Yang makes sense in this limit, but this class of a peak class makes sense. Large part of the work can be done essentially the Lee-Yang property. Lee-Yang says that the kind of characteristic functions we have is analytic, is an entire function. Is an entire function of it cannot grow more than Gaussian. So it's order 2, entire function of order 2. And because of that, we are able to do analysis, renormalization group analysis using suitable norms. And it's very important, the property of Lee-Yang. As I said, the equation we use, everything, this part we was not able to conclude, but that one also, yes, we are able to conclude. I think that's basically that. So as I said, maybe here is just one comment. I will not go too further. That's the original equation that you see when we rescaling, and we see that the n, 1 over n, when n is large, it kills the term which is second order equation. Recall that we have a heat equation. So this part comes from the heat, but there are other parts of the heat that preserve when n goes to infinity. And then when n goes to infinity, the equation turns out to a first order PDE. And this first order PDE can be explicitly solved for the spherical model. This formula here is an exact solution for the Legendre transform of that equation. But then we can recover the original from this exact solution. And most of the have understood comes from this this formula, implicit formula. And if you want to, someone want to some details, I can give you reference. Basically, I will not talk, but if we do solve the problem, and then we get the limit goes to we use the upper bound, the lower bounds to control the trajectory of the n vectorial model to close it to the fixed point Gauss. I think it's a good place to skip details.
So, comments or questions? No. So just a quick remark. Today, before the lecture of 3 p.m., we will take the picture of the workshop. So before we enter here, maybe we go outside, something like that. So just advertise. We will take a picture of you. Okay, so let's thank Domingos again.